Okay, lesson 0 from Unit 6A, rectangular approximation. I'm going to find area under curves. Finding the area between a curve and the x-axis. Imagine graphing a function sitting on your coordinate plane. Perhaps it intersects with the x-axis. We're trying to find the area contained within that region under the curve and above the x-axis. These areas are very useful for us in Calc B, but we're going to get into that story a little bit later on. For now, we're just going to talk about how we would find these areas. Example 1. Calculating area between a curve and the x-axis is easy if the curve is made up of straight lines or nice geometric shapes like a circle. So here are a couple examples. I've got a function on the left that is composed entirely of straight line segments. And as you can see, we can easily break up the areas below the curve into nice geometric shapes. I see what appears to be a square next to a trapezoid, next to a triangle. So to find the area of that region, we're just going to add up those geometric areas. In this case, it would be 9 plus 13.5 plus 18. If you don't remember how to find the area of a trapezoid, it might be worth looking that up real quick. It is something that's going to show up throughout this unit. Over on the right side, we've got this green function, and we can split it up into what appears to be a semicircle with a radius of 2, and then a rectangle. So to find the total area between that green curve and the x-axis, a fairly simple calculation. So that's all well and good. Unfortunately, most of the functions we deal with don't create perfectly straight lines or nice pieces of a circle. So we have to start thinking about what to do if the area between a curve and the x-axis is not traditionally geometric. Okay. And the strategy that we'll be using to start is an approximation technique. We're not going to get the exact correct area underneath these curves yet, but we're going to approximate using rectangles. We're going to try and construct rectangles that cover the desired area as closely as possible. And we like rectangles because obviously their areas are really easy to calculate. So, example 2, we see a curve off to the right. And feel free to pause the video and take notes or draw in rectangles as you go. But you're seeing a curve off to the right. And I've already gone in and I've constructed rectangles with an attempt to mimic the area between the original curve and the x-axis. Now, I had to make a couple of decisions here. For one thing, I had to decide how wide do I want those rectangles to be. Just to make things simple for myself right now, I'm going to go with widths of 1. That's certainly not the only possible choice. Depending on what you're trying to achieve, it's not even necessarily the best choice, but it is a choice that we're going to go with for now. So I started on the x-axis, which, our curve extends from x equals 0 to x equals about 8. We can see intersections of the curve with the x-axis at those locations. So I'm imagining a rectangle just extending from 0 to 1. That's my width of 1. Okay, you can call this region a subinterval of the full interval that we're dealing with. And then obviously the curve itself has a variety of y values between 0 and 1. So just using a best estimate, how am I going to measure this area here with the rectangle? Okay, I've got some overage area here. I've got some under coverage right here, but those regions somewhat balance each other out. I went with a y value of about 10. I also picked 10 because it's a nice, easy number to deal with. Is it the best possible approximation? Not necessarily, but it'll do for now. The second subinterval, we construct a second rectangle stretching from 1 to 2. Okay, on average, our function's y values tend to be higher in this subinterval than in the previous. So it makes sense to go with a higher height for my rectangle. Here I put it at 13. As you can see, I'm sticking with whole numbers just to make things easy on myself. Okay, and we just continue in this fashion throughout the entire interval, ending up with a total of 8 subintervals, each one with a width of 1, each one producing a rectangle with a variety of heights. And I've gone in and marked the areas of each rectangle at the bottom as well. If you were to do this on your own without looking at my attempt, it's possible you come up with slightly different heights, even if we have the same widths of our rectangles. And that's okay, because right now it's approximation. And of course, to estimate the overall area, we want to then add up each of the each of the areas of the rectangles, which I've done over here, resulting in an initial estimate of 93. So that's the technique. It is called rectangular approximation. But now that we've tried it once, we want to immediately standardize the process, because we probably don't want 20 people in class coming up with 20 different answers on a test question. So we're going to standardize the process in a few different ways. And you can see them referenced down below here: LRAM, MRAM, RRAM. Okay. I probably shouldn't overlook this notation here as well. We see a sigma notation for the first time in the course. We see an f of x, we see a delta x. This is just the mathy way of saying we're going to take a base of a rectangle, which is a delta x, multiplied by its height, which corresponds to a function height, hence f of x. I'm going to do that for each rectangle and add those up. Okay, but starting now, we're going to standardize the process, meaning we are going to come up with a rule for how you know exactly how tall to make a rectangle for each subinterval. And LRAM, MRAM, and RRAM stand for left rectangular, middle rectangular, and right rectangular approximation methods. So let's scroll this a little bit and see what each one of these is all about. We'll start with the LRAM, the left rectangular approximation. Okay. The rule here is, once you've decided how many subintervals you're going to have, within each subinterval, you have to choose the rectangle height based on what your function is doing at the left endpoint of the subinterval. Okay. And again, to make things easier on ourselves, I'm going to stick with delta x, or rectangle widths of 1 for now. We've got this blue function here. It's actually negative x minus 6 squared plus 9 if you're curious. But I've got the blue function, and again, we see a couple of intersections with the x-axis, resulting in a parabolic region that we're going to find the area of. Now, for the first subinterval, stretching from 3 to 4, if I'm going to stick with LRAM, I have to make the height of a rectangle based off of what our function's doing at the left endpoint. So in other words, what is my blue function doing when x equals 3? Well, it's kind of a weird way to start, because at x equals 3, we've got a 0 in the function. So that means we have to make a rectangle with a height of 0. And we have what's not even really a rectangle at all, just a kind of a flat line down here indicating no area. LRAM is probably not the most accurate approximation for this first subinterval, but when we do LRAM, we have to stick with LRAM. Okay. Moving on to the next subinterval, from 4 to 5, we've got a rectangle with a width of 1. Its height now has to be determined by what the function is doing at x equals 4. If you trace up from x equals 4 until you intersect the function, that's exactly where we want to draw the top of it. And it appears to be right at y equals 5. So we go with a height of 5. And then we do the same thing for every subinterval. From 5 to 6, I need to base the height off of what's happening with my function at x equals 5, where we have a y value of 8, hence a rectangle height of 8. Go through and construct a rectangle for each subinterval as I've done here. Okay, and then we're going to add up the areas. In my first pass at the work, I'm taking delta x or base lengths of 1. And instead of directly putting in a number, I'm just pointing out again that each of the heights is really a y value related to the f function. So I would call it f of 3, f of 4, f of 5. Those are the ways I would describe the heights for each of those rectangles. Once I've written that out, we can go ahead and calculate the individual areas and then get an answer at 35. If you move over to the far right side, I'm going to jump ahead to RRAM, which is right rectangular approximation. You can probably guess how this works. I've got the same subintervals as before. I've got the same function, but this time for each interval, the height is based on what's happening at the right end of the subinterval. So my very first interval, now I'm very much concerned with x equals 4. What is my blue function value at x equals 4? So we have an actual rectangle as opposed to just nothingness for the first subinterval. In fact, you get a bit of a mirror image effect due to the symmetry of the blue function as you construct these right rectangles. Eventually, the final subinterval from 8 to 9 function has a height of 0 at 9, so we have a 0 area rectangle again. And because of symmetry, it turns out that the RRAM final approximation is the same as LRAM. But let's not get ahead of ourselves. This is due to symmetry. We should not expect that LRAM and RRAM are always coming out to be the same. Now, right in the middle, we've got the third technique, MRAM for midpoint. What we're doing here, you can look again and see, same function, same subintervals, same widths and all that, but the height of each rectangle is based on what the function is doing in the middle of each subinterval. This one's a little harder to draw, but between my interval from 3 to 4, I want to know what is the function doing at 3.5. Hence, my first rectangle's area is 1 times whatever f of 3.5 is. My second subinterval, base of 1, height is whatever the function is doing at 4.5. 4.5 being in the middle of x equals 4, x equals 5. Okay. Because we're not dealing with whole numbers, there is a chance that things get a little more complicated with the calculation. Okay. Where did I get 2.75? Okay, and be careful here, because what we don't want to do is just try and estimate these heights off of the graph. We don't want to do that. We want to actually take, x equals 3.5 and plug it into that original function. Make sure you get the appropriate f of 3.5, which in this case happens to be 2.75. I'm going to repeat that one more time just to be clear. We do not want to get in the habit of using a graph and our eyeballs to estimate these heights. We want to actually plug x values into the given function to get the appropriate height for each of these. And the MRAM in this case comes out to be a little bit different than the L and the R. On homework questions, worksheet questions, test questions, you will typically be told which of these techniques to use. Okay, there might be some exceptions here or there, but for the most part, you're going to be instructed to use L, M, or R. You'll probably get some instruction about what sort of delta x's or rectangle widths to use. It won't always be 1, but you should have some idea of what you're supposed to use. On that note, let's scroll down a bit here. We see the same curve yet again in example 3, but this time we're going to go with a smaller delta x. Instead of a width of 1, we're going to go with a width of 1/2, which means we're going to have more total rectangles. We have about twice as many. Those rectangles are getting thinner. Calculation-wise, it's going to get a little bit more tedious because you've got now quite a few more x values to plug into your function to find the various heights. So it is a little bit more work, but the trade-off is you can notice visually how the areas of my rectangles here do a better job of mimicking the true area of the original curve as compared to our examples up above. So we're going to start to get improved accuracy if we're willing to commit to more and more subintervals. Again, throughout my calculation here, each of these x values has been plugged into a function. I'm not using my eyeballs to make a guess off of a graph, hence the tediousness, but it does result in a better answer. And I'll leave it to you to finish this up if you want to see what an improved accuracy looks like. Now, eventually, we will be interested in determining the actual area between our curves and the x-axis. We're not quite there yet, but I want to introduce you to the notation that gets used to find actual area. I believe it starts showing up in Delta Math. Okay, so here it is for the very first time. You see this elongated S shape with what's most likely going to be a number above and below. Those numbers above and below are giving you a clue about where on the x-axis we're supposed to be looking. We want to find area under a curve between A and B. The function that you see to the right will simply be the function whose area we're calculating under. The dx here, called the differential, indicating a couple things to us, mostly that x is the variable in question. There is a relationship between what we're seeing here and the formula on the previous page. I'm going to scroll up just a bit and remind you that even in our approximation, we see an f of x times a delta x. So there's certainly a connection between delta x and the dx that we're seeing here. But I'm getting ahead of myself. The real reason this is being introduced is just so that you can recognize it on Delta Math. Okay, example 4. Here we see one of these integral notations. We're not going to find an exact answer for this one. We're going to use approximation. Here it says RRAM, so we're going to go right rectangular. 4 subintervals of equal width. So you have to do a little mental math here. I want to extend from x equals 1 to x equals 5 with 4 subintervals of equal width. So there's a total distance of 4 divided into 4. It looks like we are going to be using delta x equals 1. Okay, so for my RRAM calculation, you can see 1, 2, 3, 4 products being added together, 4 rectangle areas. Each one has a width of 1. Okay. But then we have to think about which x values are we plugging in to this function right here to determine heights. So you have to imagine an interval from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and then take the rightmost x value of each of those intervals. So it's the 2, the 3, the 4, and the 5 that are getting plugged in to this guy right here. Go ahead and try it on your own, double check. Here are the resulting areas. If I do plug a 5 into this thing, we get back a 0. So this is one of those wonky non-height rectangles with an area of 0. But this would be the correct RRAM calculation, given that we have a certain function from 1 to 5 with subintervals of 1. Follow-up question, how would you set up MRAM? Well, if that's the only change to the instructions, we can assume we're still going from 1 to 5. We still want 4 subintervals. The only thing that changes would be the x values that we're plugging in. In my subinterval from 1 to 2, now I'm plugging in a 1.5, followed by a 2.5, a 3.5, and a 4.5. Okay. But you do want to plug those values into the listed function as opposed to trying to guess off of a graph what those y values are going to be. All right, moving along, this is going to be the last slide. Fairly common task or ask for you is to construct these estimates without seeing the function at all, without seeing a picture, just off of a table of values. Here we see a table of values. We've got a few select x values and then the corresponding y values in some function called f of x. It's worth noting that we don't actually require equal subintervals for these calculations. Oftentimes we will have equal subintervals, but it's not a necessity. I can certainly add the areas of rectangles with different bases. And in fact, that's what we're going to have to do here based on the nature of the x values we've been given. It looks like we can consider an interval from 2 to 3, and then from 3 to 5, 5 to 8. Each one of those is a different width along the x-axis. So we want to estimate this actual area or integral from 2 to 8. That lines up pretty nicely with the x values we have. We'll try RRAM, we'll try LRAM. Feel free to pause the video, try it on your own first. I'm going to go with LRAM. Well, my very first rectangle is going to stretch from 2 to 3. That's a base of 1. And its height is going to be determined by what's going on the left side of that subinterval. And of course, the height at the very left side is 4. I can read that directly from the table. That becomes the height of my first rectangle. Second rectangle, stretching from 3 to 5 in the x direction, giving me a base of 2. The leftmost function value for this second interval is 8. That becomes my height. And then finally, third rectangle, we see a distance of 3 for a width. We see a height of 10 based off of the left side, hence 3 times 10. Final calculation, LRAM approximation of 50. For RRAM, we're going to see the same widths, but different numbers plugged in for the now differing heights based off of the right f of x values for each subinterval. We see the 8, the 10, and the 5 now being used, giving us a different estimate than LRAM. All right, example 6, last little thing here. I want us to start thinking about, with these various approximations, are we able to tell in advance if we're going to be getting underestimates or overestimates? Is there a rule here? Okay, it turns out there is a rule of thumb. If I'm being honest, I don't even memorize this rule of thumb personally. If I need to, I just draw out sketches similar to what you're seeing here. You can convince yourself pretty quickly just with the sketch. Okay. In these first couple sketches, I just drew a rudimentary increasing function. The goal being to determine if I have an increasing function, which type of estimate is over, which type is under between L and RM. And in the first picture specifically, I know it's a little rough, but I'm trying to draw rectangles whose heights are based on the left side. So we see LRAM function is always increasing, So if you just think about it, it makes sense. The LRAM, okay, the height on the left side is going to be less than the height on the right side because your function's always getting higher, higher, higher. So it makes sense that my rectangles always come up short. They all live below the actual upper boundary of the curve, resulting in underestimates. And I've notated that in my chart off to the right here. If I have LRAM with an increasing function, you always get underestimates. Second picture, now I'm going with RRAM rectangles. Your heights are based off of the right side. Function is increasing, so the right side is taller than the left side. All my rectangles are now over. RRAM with increasing function gives you an overestimate. And it shouldn't surprise anyone that those rules flip when you switch to a decreasing function. I've got my LRAM sketch here. I've got my RRAM sketch right here. And you can see for yourself how that works. So you can memorize it if you like, but again, for me, it's not worth the trouble. Just draw a quick sketch if you need a refresher. If you have any questions on lesson 0, feel free to email me or ask me in class. That concludes the video. Thank you for watching.